Alright, so in this lesson we're going to look at the pendulum in a little bit more detail and talk about what is a pendulum first of all, and then what are some things that we can look at when we analyze the pendulum that allows us to treat the pendulum as simple harmonic motion. So pendulum is really any type of device that's created by having a massive object swing back and forth. Usually we'd use a string or a rod to do this. In this case I've said that this is a nearly massless rod. It has a pivot point and we have a massive what we call bob at the end. So this thing is much more massive than the bob itself. So if I pull this back some amplitude theta, some angle, and release it, it's going to swing back and forth. And we're going to call this the equilibrium position straight down. And so the amplitude is how far have I twisted it this way. If we look at the forces that act on the bob, we have the weight of the bob acting down, and we have the tension in the string acting up. So it's really a component of this tension that is causing this object to accelerate. If we use the equation F equals ma, well, the net force is acting toward the center here. We could say sum of forces in the y direction is equal to 0. So we can actually figure out how big the tension is. Tension force times cosine of theta minus mg is 0. And tension force in the x direction times sine of theta equals ma, the acceleration. So we can actually solve this out for what the tension force looks like, that it's the weight divided by the cosine of theta. Now if I take and substitute that in there, what I get is an expression mg tangent of theta equals ma, where this acceleration is really dependent upon this angle theta. How far is this thing swung back and forth? Now the one thing to point out is if theta is small, so we're talking about an angle less than maybe 10 or 15 degrees, the tangent of theta and the sine of theta are basically the same thing. And the sine of theta would be x over L, where x is this distance here and L is the length of the pendulum. So you're going to take and substitute that in here and cancel out the m's. And so really what this looks like is that your acceleration is dependent on the length of the pendulum and this distance x. How far away from the equilibrium position in the horizontal direction did you go? Now if we apply what we already know about simple harmonic motion, that if I make x a sine of omega t and acceleration a omega squared sine of omega t and cancel some things out, what we're left with is that omega squared is equal to g over L, or omega is equal to g over L. What this is going to tell you is that the frequency and the period of this motion only depend upon two factors. They only depend upon the acceleration of gravity g and the length of the pendulum. Longer pendulums, longer periods, shorter frequencies. If we managed to go to a different planet and change g, we could change the frequency or the period of a pendulum on a planet. In fact, one trick that was used by astronauts in the Apollo mission to measure the acceleration of gravity on the moon, they carried a pendulum with them and measured the period. They knew the length, they could measure the period, and so they could verify g for the moon, what we thought it was. So let's kind of do a quick similar, I guess, problem. Here we have a pendulum that's brought by a space probe to measure the acceleration of gravity on Mars. And it's worth pointing out that this has actually happened. On one of these space probes that we've sent to Mars, there was a pendulum on there. We brought it up there just to measure the acceleration of gravity. Pendulum is tested on Earth before launch and it's found to have a period of 2.46 seconds. When the space probe lands on Mars and conducts its pendulum experiment, it finds that the pendulum now has a period of 3.97 seconds. And it wants to know what is the acceleration of gravity on Mars. So some things that I can say right away: the period on Earth is 2.46 seconds, period on Mars is 3.97 seconds, and I know the length of the pendulum doesn't change. I'm using the same pendulum, so the length on Mars and the length on Earth would be the same. Well, if 2 pi times the square root of L over g is equal to period, I could maybe solve this thing for the length and get some ratio of period to g. So my first step in solving for length is I'm going to square everything, and then I'll multiply by g and divide by 2 pi squared. And so the length is equal to period squared times g divided by 2 pi squared. So this would mean is I could say period squared on Earth times g on Earth over 2 pi squared equals period squared on Mars times g on Mars over 2 pi squared. Now the 2 pi squared cancels out, it's a constant. So period squared times g equals period squared times g. The only thing I don't know is this one, because I know g on Earth is 9.8. So if we solve it out, we end up with is that the period or the acceleration of gravity on Mars is 3.76 meters per second squared. We could go look that up on Wikipedia, and you'd find that's pretty close to what the accepted value for the period on Mars is, or for the acceleration of gravity on Mars. So that's kind of a quick overview of the pendulum. The one thing to point out is that we get, let's go back to this slide here all the way to the end. We get some nice equations for frequency and period and angular frequency for a pendulum that look very similar to those equations that we had for a spring. Mathematically, these look like identical systems. The only thing that really changes is what are the variables inside here. Instead of k and m, it's g and l. The other thing to point out is that the mass of this end does not influence the period of the pendulum at all. It could be a 50 gram mass, a 50 kilogram mass, a 50 ton mass. As long as they all have the same length that are on Earth, all of them are going to act exactly the same.